Here's your lesson on related rates. Okay, with the chain rule, you can now take the derivative of an equation with any variable with respect to any other variable. Okay, let's try one. Give the derivative of the equation with respect to n. So here's my function, and what I'm asking you to do is find dn. I'm asking you, how does this function change as n changes? Okay, that's what this means. It's basically a slope. Remember, the derivative is a slope. So I'm saying, how does this thing change with respect to n? If you consider n as what the thing that you're based on, like time, miles per hour. Okay, so that's going to be your rate. And we're going to identify variables, constants, and operations. And I've labeled them in color here. The blue are our variables. Okay, the red are our constants that don't change, constants and coefficients. The 3 is a coefficient and 7 is a constant. And then the operations is the squared and the plus. Okay. So we're going to use the chain rule on the variables. And we're really doing this. We haven't done anything yet. I just wrote the notation. We're gonna remember, this is the verb, right? So we're gonna do this on this and this. And I always like to move coefficients out of the way so I can take the derivative and then put that on afterwards. So using the chain rule on m, we get the derivative of m is 1, but then we have a dm dn is equal to, take the 2, put that in front with the 3, that's a 6, that's n to the 1 power, then that's dn plus, and then the derivative of any constant is 0. And I don't normally write this here because that reduces to 1. So that means as m changes with respect to n, that's going to be equal to 6n. Okay. Let's try one that's a little bit more complicated. Okay, give the derivative of the equation with respect to t. So now we're going to figure out how this thing changes with t. And this doesn't matter in this problem here, but t usually represents time. So if we're doing this, we're probably trying to figure out how does the volume, okay, of this thing here change with respect to time. And this is actually a cylinder, or actually a cone. Yeah, this is the formula for a cone. So we want to, over time, how does this cone change if the radius and height are on this side? So we're going to find dt. So we're going to identify which are our variables, and we have 3 variables here, and 1 coefficient and an operation. And we're going to use the chain rule. So this is just before I start. I'm going to move the coefficient in the front, so I can just take the derivative of this, and get to recognize the fact that you have 2 variables multiplied together here. That means that this is the product rule. We have r times h, r squared times h. So here's dv dt. Okay, then the product rule, the first times the derivative of the second, derivative of h is 1, dh dt, plus the second times the derivative of the first, which is 2r times dr dt. Just cleaning this up a little bit, and then there's our answer. We have a lot of things that we don't know. Normally we would have something else in here. They're either going to give you r, h, the rate that the radius changes with time, or the rate that the height changes with time, or the rate that the volume changes in time. So only one of these things will be unknown. Or maybe if 2 of these things are unknown, then they'll give you something else to help you solve for another unknown. So this is an unknown here. This is an unknown. This is an unknown. This is an unknown. This is an unknown. And this is an unknown. So we have 1, dv dt is an unknown, r is an unknown, dh dt is an unknown, h is an unknown, and dr dt is an unknown. So now we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 unknowns. Okay, let's do a problem. Now I'm going to start going into these word problems here. Suppose that x and y are both differentiable functions of t and are related by the equation y is equal to x squared plus 3. Find dy dt when x is equal to 1, given that dx dt is equal to 2 when x is equal to 1. There is no context to this problem, which makes it a little bit more difficult to understand. But let's break this apart here. The first part here, suppose x and y are both differentiable functions of t. That just tells you that you're allowed to take the derivative of this, right, if they're differentiable. Okay, that means it's possible to take the derivative of this. So you can ignore that. And with respect to t, that means we're going to do everything with respect to t. That's dt and the denominator on everything by this equation. So that's just nothing. That whole first sentence line there really is nothing. Here's the function. And then we're going to find dy dt. This is my derivative. We're going to find everything, or we're going to find the change in y as change in t. We're trying to find how does y change when t changes. Then they give you a condition when x is equal to 1. You remember there was like 5 unknowns in the last problem? Now they're going to give you some of them, okay? They're telling you x is equal to 1. And they're also telling you that dx dt is equal to 2. So they're giving you another piece of information when x is equal to 1. So they say that this kind of goes with this, okay? Well, not kind of, it does go with that. So let's do our job here. We're going to take the derivative of this function with respect to t. Taking the derivative of y with respect to t is just dy dt. Then I take the derivative of x squared and the 3. 3 is a constant. We don't worry about that. So this is going to be 2x dx dt. Notice that these don't cancel. Before we had one of these cancel. This is it. This is our derivative. But they want us to find dy dt, which we found when x is equal to 1 and when dx dt is 2. So they gave us everything. So they want us to come out with a final number answer. So we're going to put in 1 for x, and then we're going to put in 2 for dx dt. Okay, so we're going to put in dx dt for 2 for dx dt, and put in a 1 for x, and then we have this. We finish this and we get a 4. Final answer. How's that? All right, now let's do one in context. Wait, before we do the one in context, let's do this one. Oh, this one actually is in context. A point is moving along the path of a given function such that dx dt is 2 centimeters per second. Find dy dt for the given values of x, for this value of x. So we have a parabola, right? And a point is moving on our parabola at a rate of 2 centimeters per second on the horizontal axis, dx dt. We want to know how does it change on the y-axis. All right. So we're going to take our derivative. Applying our derivative, we get dy dt is equal to 2 times 2 is 4x dx dt. The 1 goes away because the derivative of a constant is 0. They gave us x is 1, and they gave us dx dt is 2. So we're going to put those numbers in, and we'll get 8. But what is that? Make sure you put the units back in, because the units are very important on the AP test. One of the questions will just be, what are the units of the answer? Or what are the units of a certain part of the problem? You will see that when we start practicing on the actual AP tests release questions. Okay, units are very important. All right. Let's try this one. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Here's a graphic of that, as shown in figure 2.34. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. Every second, this ripple is traveling a foot. So the circle is getting bigger and bigger and bigger. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So they want you to find the inside area of that circle when the radius is 4 feet. Now this is actually a actual calculus problem. I bet you all through your school you go, what is calculus like? What is calculus like? Now this is where calculus comes in, and this is where no other math can attack this problem. Okay, so what do you need here? You need to know that you're working with a circle. Okay? And we need to know that we want the area of a circle. So you need to know that formula for an area of a circle. You notice they didn't give you any formulas in here. So we're going to have to know that A is equal to pi r squared, not given on the AP test. Okay? And you have to know that r is equal to 4. This is stuff that they're giving you here, 4 feet. And then you have r is the outer let me back up here. And the radius is increasing at a rate of 1 foot per second. That means the radius is increasing at a rate per time of 1 foot per second. You notice that r is in feet and times in seconds. The units will look like what you're trying to find. That's why the units are important. Okay, what are we trying to find? Always write this. I gotta, students try, they do this, or they try to do this, they take the derivative, they're adding, subtracting, and then I'm going, what are you trying to find? They go, I don't know. So what are you trying to find? It's usually the last sentence in the problem, and it says, when the radius is 4, what rate is the total area of the water changing, disturbed water changing? So we're trying to find the area as a rate of change. So that means we're trying to find the change in area with respect to time. Okay? Alright. So now we're going to take the derivative. So when we take the derivative, we get dA dt. That's what we're trying to find. And then the only variables are here, so the pi is a constant. We take the derivative of r squared, which is 2r. Don't forget the dr dt from the chain rule. And then they gave us everything we need to find to get this. So we can put in the 4 and the 1. And our final answer is 8 pi feet squared per second. Remember, the area of a circle is in feet squared. Area is feet squared, or centimeters squared, or inches squared. And time, in this case, is in seconds. Okay. How is that? Okay, this is just the beginning of your nightmare. All right. Okay, these get kind of complicated, so your book gives you this little list here. You may want to copy it down. Some people like them like this, but how I learn them is just through a lot of practice and practice and practice. but some people like a list, and then there are not very many list steps in calculus because every problem is so individualistic and unique. But they want you to identify the given quantities, okay? And then what are you trying to determine? Make a sketch and label the quantities if needed. I always make a sketch. Write an equation involving the variables. So in the case of the last problem, we need the a is equal to pi r squared, okay, whose rates of change either are given or are to be determined. Use the chain rule, implicitly differentiate both sides of the equation with respect to time. These are usually rates of time, okay, and after completing step 3, substitute into the resulting equation all known values. The biggest mistake students make when they're doing these problems is they say, oh, x is equal to 5. They plug in the 5 into x, but when you find out that x is changing, you're not allowed to plug in that 5 until the very, very end. Okay, that 5, when you take the derivative, that x will change. It will go from an x squared to an x, or x cubed to a 3x squared. So that x is going to change. Do not plug in your numbers until you know what you're plugging in. Okay, you can plug in things that don't change, but you cannot plug in things that are part of the variables that are changing. Then solve the required rates of change. Okay, so to help you understand the reading part, here's a little thing that I found in your book. The velocity of a car after traveling for 1 hour is 50 miles per hour. Okay, this is what they might say. This is what they mean. X is the distance traveled, and the change in the distance, miles per hour, is equal to 50, right? Miles per hour, when time is equal to 1. This is what they're trying to say. Water is being pumped into a swimming pool at a rate of 10 cubic feet or cubic meters per hour. Okay, use a variable to represent the volume. V is a good variable for volume of the water. And then the change in volume is 10 cubic meters per hour. How did you know that to use a V here? Because the water is being pumped into a pool, and the water is going to take up volume. It's going to take up cubic something. It's not going to take up area. It's going to take up volume, right? It's not going to be flat like an area. It's going to take up three-dimensional space, which is volume. A gear is revolving at a rate of 25 revolutions per minute. 1 revolution is 2 pi radians. All right, this I'm surprised they gave you here, because 1 revolution, this is actually just circumference. C is equal to 2 pi radians. All right. So here you have the angle of revolution. Okay, 1 full revolution would be 2 pi, right? You should know that 1 full way around the unit circle is 1 revolution, which is 2 pi, right? Around the unit circle is 2 pi for 1 time around. So the angle, the change of the angle, and in this case would be in radians over time, is equal to 25 revolutions times 1 revolution per minute, right? So in this case, do not use degrees, because this will all fall apart. Okay? All right. Here's one more problem that we'll do together. Air is being pumped into a spherical balloon at a rate of 5.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Seems kind of like a gibberish right here. Find the rate of change of the radius. Okay, so what we're trying to find is dr dt when r is equal to 2. Can you see that? All right. Air is being pumped into the balloon at a rate of 4.5 cubic feet per minute. So the cubic feet per minute tells you we're talking about volume. Okay, so here we go. The volume of a sphere is 4/3 pi r cubed. Get used to looking at this, maybe write it down somewhere, try to memorize it. They may give it to you on the AP test and they may not. Okay, I think they probably will, but it looks like a circle, right? Except it's 4/3 of a circle and then multiplied by r again. Like the area of a circle is pi r squared. This is 4/3 pi r cubed. Okay, now we want to find the change, the rate of change. Find the rate of change of the radius. We're given the rate of change of the volume, okay, which is dV dt is equal to 4.5 cubic feet. Ooh, I left out a cube there. Okay, there should be a cube there. Maybe let me put that in there quickly before you get confused or I get confused. Okay, and then okay, and then what else do you know? You know that r is equal to 2. So we're trying to, nothing else is given, right? We've used all the information given. We even pulled out our own formula. We used the two numbers they gave us. So now we're going to find the derivative. Find the derivative. What are we trying to find? We're trying to find the rate of change of the radius. So we're trying to find dr dt when r is 2, at r is equal to 2. Okay, finding the derivative. Take the derivative of v is the volume formula. So on the left side we have dv dt is equal to, I'm going to move that 4/3 out of the way, 4/3 pi. Take the derivative of pi r cubed, take the derivative of r cubed, which will be 3r squared dr dt. Now we've got these two pieces of information. We can solve for our unknown, which is dr dt, the rate of change of the radius with respect to time. So now this is going to be just some algebra here, and here this is 2 squared times 3 is 12. You can do some creative work in here and get that to 16, reduce the 3 and the 12, multiply by the 4, divide both sides by 16 pi. Now, normally if we have pi, we leave it as pi, but since pi is in the denominator, that doesn't make any sense, so that's not like how many pi. So we're going to go ahead and finish this with a decimal, and that's our final answer. Units are important. Radius is in feet, not in feet squared or feet cubed, and time they gave us was in minutes. Okay, so let me see, I made a mistake up here. I didn't catch it earlier. The radius is not in 2 feet per minute, it's just 2 feet, no minutes on that. Okay, just in feet. Just notice that when I look down here, the units were the same, which didn't make any sense to me. Always look at the answer and make sure it makes sense with what's given. Otherwise, you did something wrong. Okay, there's a few problems I want you to try in the book, and then that's it.